Here we've got Rolle's theorem. Sometimes it's a little bit hard to read, and the best way is just to start making an example, understand what they're saying. So let's start off with an axis. So I've got my x and y on here, and then it says f is continuous on AB. So let's get a point A and a point B on here. And so I'm going to draw a continuous graph, but we've got a restriction right here that says f of A is equal to f of B. That means that if I pick a point to be my f of A, so right here, this has got to be the same value for f of B, right? These two guys have got to line up. So they both have, my f of B is the same value as my f of A. So that's our restriction that's put on this theorem. And so now what Rolle's theorem says is that no matter what kind of curve I have, whatever I put through here, there's got to be a place on here somewhere where this tangent line has a zero slope, right? So we're saying that this is the point C that he's referring to here, where f prime of C equals 0. So the derivative at this point is 0. Well, there's actually no way I can draw a curve that connects these 2 points without somewhere in between there being a point where the derivative is 0. I can back this up and try it another way. Maybe we do it this way. Well, try my pen. I still have a point, this time it's here. So now there's my point C, where this tangent line is 0. I could draw, just a straight line through there. Well, there's a bunch of points where the tangent line, an infinite number of points where the tangent line is 0. But you get the idea that if these two values, if those two are equal, that's kind of the key to the whole thing. If those two are equal, somewhere in between there, the tangent line is going to have a slope of 0. Well, that goes one step further with this mean value theorem. It applies to some more situations. This one's actually saying that the derivative is equal to what we'll call the overall slope. From A to B. There's got to be a point in there, not where it's just 0, but where it's any slope that there is for A and B. So now we're saying f of A doesn't have to equal f of B. We take our same situation, we give ourselves an A and a B, and I just draw any graph I want through here. Well, I have a value that is f of A, right? I have a value over here that is f of B. And if I connect them, let's see if I can do this. The slope of this line will be f of B minus f of A over B minus A. Just what we're saying right there, the slope. Well, somewhere in here, I can find a tangent line, it's like maybe here, where the slope matches, right? Those two lines both have the same slope. And so this would be the point C that's referred to here, this C. So that f prime of C is equal to that same slope. The slope of the tangent is the same as this overall slope that's going from point A to point B. So hopefully that makes sense. If we wanted to look at an example, we could look at something like this. We're supposed to essentially show where the mean value theorem applies, and it's find this magic value C where this happens. So I would want to do two things. I like to think of this in two different pieces. It's split, right? So if I'm checking this, over here, I'm looking at calculus. I'm doing a a derivative. Over here, I'm finding an algebraic slope. So that's just delta y over delta x. So if I find the derivative of this thing, if I'm looking for f prime of x, remember that 4 over x, that's the same as 4x to the negative 1 power, right? And so 5 minus 4 over x, when this negative 1 comes into the front where this negative 4 is, I'm going to get a positive 4x to the negative 2 power, or I can write that as 4 over x squared. Over here, I've got an actual slope that I'm finding, right? So f of 4 is 5 minus 4 over 4, which is 4. And f of 1 is 5 minus 4 over 1, which is 1. So for this slope, I've got 4 minus 1 over 4 minus 1, just gives me 1. Well then, our connection here is that those two things need to be equal. So if I'm trying to show where the mean value theorem applies, I take my result from this side, 4 over x squared. Wow, didn't write that very well. And I set it equal to my result from this side, 1. And then I get that 4 is equal to x squared. So if I solve this for x, I'll get that x is equal to plus or minus 2. Now, if I go back up to the problem, and I look, what is it they're asking me for? I'm looking for all values, so that's all x values, but on this interval, 1 to 4. Well, the only one of these two that's on 1 to 4 is x equals 2. So x equals negative 2 is the right answer. It's just not on the interval that we're looking for. So what this is saying is that when x equals 2, the derivative matches the slope from x equals 1 to x equals 4. If you're having a hard time visualizing that, don't worry. I got your back. Here's a graph of what we were just looking at. So this is our function here in red. We've got f of x. We found a slope that went from here, x equals 1, to x equals 4. So we found the slope of this line. And we found this slope to be 1. And then we found the derivative, which gives us the slope at any point x. Well, we wanted to know at what point was this derivative equal to 1? Where did it match with this slope here? Well, the answer we got was at x equals 2. Well, check it out. It's perfect. We've got our tangent line of this line that matches the slope of the green line. It's tangent at exactly x equals 2 on f of x. So you kind of see how it fits together and what it is we're looking for. Just one more way to see how this kind of fits together. I'll put a little demonstration on here where I just took a random f of x, and we've got point A and B, and I drew a line for the slope from A to B. What I want you to see is that there are actually two places in this example, in between A and B, where the slope of the tangent line matches. And the way I can do that, or show you that, is I can grab one of these lines, and I'm taking the exact same line, and I can just move it up here until it's tangent. And so I can see that this right here, this is one of the point C's that's referred to in the theorem. There's actually another one, if you look right there, I get another point C. So we could call this like C1 and C2 or whatever, but you can see the idea there that I'm taking the exact same line, and the theorem just guarantees that as I move that line around, I will find a spot on this graph somewhere. Generally, the way the problems are going to be asked of you is that you're going to be trying to determine what is the value of that point where it does actually line up that way.